Hi. In this problem, we are asked to find the volume of the tetrahedron bounded by the coordinate planes and the plane 3x plus 3y plus z equals 3. So let's get an idea of what's going on. So you have the coordinate planes, and then you have this other plane, 3x plus 3y plus z equals 3. And we want to find the volume of this. Well, we know how to find the volume of a solid that's under the graph of a function z equals f of xy. So I can rewrite this as z equals 3 minus 3x minus 3y, right? So I have this function of x and y, and I'm trying to find the volume of this solid that's bounded by this the graph of this function. So I need to see, since this tetrahedron is bounded by the coordinate planes, I want to see where this plane is intersecting the x, y, and z axes. So where does it intersect the different axes? Where does it intersect the x-axis? X-axis is when y and z are 0, right? So when y and z are 0, you get x equals 1. So this intersects the x-axis. When y is 0 and z is 0, you get 0 is 3 minus 3x minus 0. And then this ends up giving you x equals 1. So the plane intersects the x-axis at x equals 1. And where does it intersect the y-axis? Well, that's when x is 0 and y is 0. You're going to get that's when x is 0 and z is 0, and that's when you get 0 equals 3 minus 3 times 0 minus 3y. That 0 is 3 minus 3y. That's when y is 1. Okay? And then where it intersects the z-axis, that's easy, right? X and y are 0. You plug those in, you get z equals 3. So this plane goes through these 3 points, and you only want the part that's in the first quadrant because it's bounded by the coordinate planes, and that's the tetrahedron that we're finding the volume of. All right, so when you have something of the form z equals f of xy, which is what we have, right? We have this. We need to integrate. Well, one way to do it is to set up a triple integral. There's 2 ways of doing it. You could set up a triple integral where you integrate 1 over the solid, or you can replace it by a double integral where you do the double integral over a certain region, which is the region that you get by projecting this graph to the xy plane. And when you do that, the projection onto the xy plane is going to be this triangle here. So let's draw it. Let's draw the 2D version of it. It's going to be like this. It's this triangle R that goes through that has the origin and 1, 0 and 0, 1. And you're integrating the function z equals 3 minus 3x minus 3y over this triangle. So the volume of the tetrahedron is the double integral over R of 3 minus 3x minus, 3 minus 3 minus 3x minus 3y dA. That's the double integral we want to solve. And to do this integral, we can set it up as iterated integral, right? That's the Fubini's theorem. The values of y, you have this line here, and then you have this line here, and this line is y equals 0, and that line, so this is a line that goes through 1, 0, and 1, 1, so it's going to be x plus y equals 1, or y equals 1 minus x. Right? I mean, the slope is negative 1, and the y-intercept is 1, so you get this, and then x is going from 0 to 1. So now we can set up this double integral as an iterated integral. You first integrate from 0 to 1 minus x with respect to y, and then you integrate with respect to x, and x goes from 0 to 1. So now we just need to calculate this integral. So let's do the inside integral first. We have to integrate 0 to 1 minus x, 3 minus 3x minus 3y with respect to y, and that's going to give us 3y minus 3xy minus 3 halves y squared from 0 to 1 minus x. And that's going to equal, we plug in the bounds for y, so it's going to be 3 times 1 minus x minus 3x 1 minus x minus 3 halves times 1 minus x squared. And then when you plug in 0, right, you have to subtract what you get when you plug in 0, but you're just going to get 0 minus 0 minus 0, so you just get 0. Now we have to integrate this with respect to x. And to do this, we have to first, okay, this is going to be kind of time consuming because we have to distribute the whole thing. There isn't really a shortcut. So it's going to be 3 minus 3x minus 3x plus 3x squared minus 3 halves. And then this is going to be 1 minus 2x plus x squared. Okay, what do we get? So we get 3 minus, so we have minus 3x minus 3x. So that's going to give us minus 6x plus 3x squared, and then minus 3 halves, and then plus 3x minus 3 halves x squared. And now let's simplify a bit more. Let's collect the x squared terms. 3x squared minus 3 halves x squared. So 3 is 6 over 2. When you subtract 3 over 2, you get 3 over 2 x squared. Now let's collect the x terms. Minus 6x plus 3x is minus 3x. And then 3 minus 3 over 2 is 3 over 2. So that's the inside integral. And now we just need to do this integral, right? We found the inside integral. Now we just need to integrate that from 0 to 1. So when you integrate from 0 to 1, you see what you're left with is just an ordinary integral that you've done before. So this is going to be 1/2 x cubed minus 3 halves x squared plus 3 halves x from 0 to 1. And when you plug in 1, you get this. You subtract what you get when you plug in 0, that's 0. And then this is going to be 1/2 minus 3 halves plus 3 halves. And then everything, the 3 halves and 3 halves cancel, and you get 1/2. So that's the volume. So let's just review what we did. The first thing to do is to get an idea of what the tetrahedron looks like so we can set up the integral to find the volume. And we rewrote this as a function, z, as a function of x and y. Then you have to see, since in this question the tetrahedron was bounded by the coordinate planes, you have to see where the plane intersects the x, y, and z axes. And once we did that, we were able to see what the tetrahedron looks like, and we were able to see that the region below it is this triangle. And from that, we were able to set up this double integral. Then you set up the bounds, right, with your picture, and then you do the integral, the iterated integral, and then you get the answer. Okay. So this is an example of using integrals to find volumes. You could also have done this as a triple integral of 1 over the solid, but when you do the triple integral, the inside integral will just be 3 minus 3x minus 3y. So it ends up being the same thing anyway. Okay, thanks.